Today we're going to talk about derivatives in complex analysis. Now, the way we define the derivative for a complex valued function is the same structure as we use to define the derivative for a real valued function. So if I have a complex function f of z, then I say it has a derivative at z equal to z naught if the limit of the difference quotient, that is f of z minus f of z naught, divided by z minus z naught as z approaches z naught exists. In that case, it will be called the derivative of the function f at z naught. This definition alone leads to some pretty obvious results. For example, if I define f of z to be some fixed complex number c, then the derivative of the function f is going to be 0. And if I define f of z to be z to the n, where n is some integer, then the derivative of the function f would be n times z to the n minus 1, the classic power rule we all know and love. And this power rule can be proved from this limit definition using the binomial expansion. And there are some functions that you just can't differentiate. For example, if you define f of z to be z bar, as in you feed the function a complex number and the function will just spit out the complex conjugate, this function is just not differentiable. For proof why this function isn't differentiable, recall that a function f is differentiable only if the limit of the difference quotient as z approaches z naught exists. So if we fix f to be z bar, that means we're evaluating the limit as z tends to z naught, terribly sorry about that, of z bar minus z naught bar divided by z minus z naught. Okay, now does this limit exist? What does it even mean for a limit to exist? The limit exists if, regarding the complex number z naught, we can approach it along any possible route in the complex plane. No matter what route we choose, the value of the limit should be the same, as in the limit needs to be path independent. That's what we mean by limit existing. So let's evaluate the limit along two distinct paths. One is along a horizontal line through z naught. So approaching z naught along a horizontal line means that every complex number on this straight line has the same imaginary part as z naught. So writing this limit as the equivalent limit of delta z bar, where delta z is the difference between z and z naught, divided by delta z, as delta z approaches 0, we see along this path, along this horizontal line, delta z is just the difference between the real parts of z and z naught. So in this case, the complex conjugate of the difference is equal to delta x as well, because delta x is a real number, so it's equal to its own complex conjugate. So that means the limit of z bar minus z naught bar divided by z minus z naught as z approaches z naught equals the limit of delta x by delta x as delta x approaches 0. So in this case, we get a 1. Okay, now let's take a different path, and that different path is along a vertical line through z naught. So approaching z naught along this vertical line, the difference between z and z naught equals the difference in their imaginary parts. So that would be I times delta y. So in this case, the limit of z bar minus z naught bar divided by z minus z naught as z approaches z naught equals I times delta y bar divided by I times delta y in the limit as delta y approaches 0, of course. And we know what the complex conjugate operator does to the imaginary part of a complex number. It just introduces an extra negative sign. So here's our extra negative sign, some cancellation once more, and now we get a -1. So we see here that choosing a different path to evaluate the limit results in a different result. So the limit does not exist, and we conclude that this function here is just not differentiable. A well-known theorem in real analysis is that differentiability implies continuity. And this theorem holds in the complex realm as well, as I'm going to prove right now. So the proof lies in the fact that f of z equals f of z minus f of z naught, where z naught is a point where f of z is differentiable, divided by z minus z naught times z minus z naught to balance that out, and to balance it all out, we have to add f of z naught as well. Yeah, now this looks like we're actually going to put in some work into a proof. So taking the limit as z approaches z naught, the limit of this thing here is exactly this thing. It's just a complex number f of z naught. And the limit of this thing as z approaches z naught is the derivative at z naught. And this thing in the limit as z approaches z naught evaluates to 0. So we get the result that the limit of f of z as z approaches z naught equals f of z naught, which means that differentiability at z naught implies continuity at z naught as well. The same old rules from real analysis that we know and love about derivatives carry forward into complex analysis. So there's a sum or difference rule. There's a constant multiple rule for any fixed complex number C. There's a product rule and quotient rule, and all the rules are exactly the same in structure as the ones from real analysis. And there's also a chain rule, again identical in structure, where we define g of z to be w, and g at z naught, let's call it w naught, where z naught is a point where the derivative of g exists. And we define another function, f of w, that is f of g of z, and the derivative of the function f at the complex number g of z naught, that is w naught, exists, then we have this relation for the derivative of the composite function f of g at z naught. And the proof is pretty cute, I would say. It's a very cute little proof. So what do we mean by the derivative of the composite function at z naught? By that, we mean we're evaluating the limit as z approaches z naught of f of g at z minus f of g at z naught divided by z minus z naught. So let's just expand on this a little bit. I'm going to write this as the limit as z tends to z naught of f of g of z minus f of g of z naught divided by something, and something divided by z minus z naught. And that something is g of z minus g of z naught, and I have g of z here and g of z naught here as well. So what exactly is this structure in the first difference quotient evaluated in this limit? Well, this would in fact be, this is equivalent in fact to the limit as g of z approaches g of z naught, or w approaching w naught if you would like, of f of g of z minus f of g at z naught divided by g of z minus g of z naught. And this other structure is the limit as z tends to z naught of g of z minus g of z naught divided by z minus z naught. The derivatives exist, so yeah, the limit of the product equals the product of limits. So the first thing we have here is the derivative of the function f evaluated at g of z naught. And the second limit we have is the derivative of g evaluated at z naught, which is exactly what we set out to prove, correct? So that does it for the lecture on derivatives of complex functions. Stay tuned for next time where we're going to be discussing in detail analytic functions and the conditions for which a function is analytic. It's extremely important, a very, very important topic in complex analysis. Make sure you don't miss it. Be sure to like and subscribe. Thank you. See you next time.